The initial mass function, IMF, is one of the most fundamental concepts in modern astrophysics, serving as a cornerstone for our understanding of star formation, galaxy evolution, and the universe's chemical enrichment. This report provides a detailed exploration of the IMF, its physical origins, observational evidence, and far-reaching implications for astronomy. The stellar initial mass function, IMF, is defined as the distribution of stellar masses that form in a given region during a single starburst event. It represents a probability density function that describes the likelihood of a star forming with a particular mass. This seemingly simple distribution function has profound implications across astronomy, as it is key to reconstructing the cosmological matter cycle, understanding the formation of supermassive black holes, and deciphering the light from high redshift observations. The IMF serves as a crucial bridge between theory and observation. It represents a fundamental output from theories of star formation, while simultaneously functioning as an essential input to models of galaxy formation and evolution. It allows astronomers to convert between observed luminosity and the underlying stellar mass, making it possible to connect extragalactic observations with simulations. Some researchers have even described the IMF as perhaps the greatest source of systematic uncertainty in star and galaxy evolution, highlighting its critical importance. Understanding the IMF is vital because a star's initial mass largely determines its entire evolutionary path. The mass of a star at birth is the primary factor determining its color, luminosity, radius, radiation spectrum, and the quantity of materials and energy it will emit into interstellar space throughout its lifetime. The relative abundance of stars in different mass ranges profoundly affects various measurable properties of stellar populations. While low-mass stars contribute most of the stellar mass, massive stars dominate the luminosity, and along with intermediate mass stars, are responsible for enriching the interstellar medium with metals. The conceptual foundations of star formation trace back to Isaac Newton, who first proposed the idea of gravitational collapse as a mechanism for stellar birth. However, the systematic study of the stellar mass distribution began much later, developing significantly during the 20th century. The field has evolved through extensive observational work and theoretical modeling. Comprehensive reviews of the IMF literature have been presented by numerous researchers, including Miller and Scalo, and Krupa, each building upon previous work to refine our understanding. These reviews have helped establish the foundational knowledge about the IMF that informs current research. The IMF is commonly expressed mathematically as a power law or a series of power laws covering different mass ranges. In its most general form, the distribution can be written as dnd log mmgimf, where n is the number of stars, m is the stellar mass, and GIMF is the power law index that may vary across different mass ranges. Depending on various physical parameters such as the Mach number and density distribution, several regimes of GIMF have been identified, including values around 0, 0.8, 1, or 1.3. While these mathematical regimes appear to be universal in nature, the transitions between them can vary depending on environmental conditions. The IMF differs from the present-day mass function, PDMF, which describes the current distribution of masses of stars in a given population. The PDMF includes evolved stars such as red giants, white dwarfs, neutron stars, and black holes, reflecting both the initial distribution and subsequent stellar evolution and mass loss. These two functions can be connected through the stellar creation function, defined as the number of stars per unit volume of space in a mass range and a time interval. For certain populations, particularly those where stellar lifetimes exceed the age of the system, the IMF and PDMF are effectively equivalent. This is notably true for brown dwarfs, which have unlimited lifetimes due to their inability to sustain hydrogen fusion, making their present-day distribution a direct reflection of their initial distribution. The IMF exhibits several distinct features across different mass ranges, each reflecting different physical processes in star formation. The high-mass portion of the IMF typically follows a power law behavior, originally characterized by Edwin Salpeter. This region of the distribution is believed to be primarily shaped by gravity and turbulence in the star-forming gas. High-mass stars, while relatively rare, have disproportionate effects on their surroundings through intense radiation, stellar winds, and eventual supernova explosions. A critical feature of the IMF is its peak, which occurs around 0.1–0.3 solar masses. This peak represents the most common stellar mass produced during star formation events. Recent research suggests that this characteristic mass may be a consequence of dust opacity and molecular hydrogen physics at the origin of the first hydrostatic core, the initial stable configuration that forms during protostellar collapse. Importantly, this peak appears to depend only weakly on large-scale environmental conditions such as radiation fields, magnetic field strength, turbulence, or metallicity. This relative insensitivity to environmental factors may help explain the observed uniformity of the IMF peak across diverse star-forming regions. Below the peak, the IMF flattens significantly, indicating a declining probability of forming very low-mass stars and brown dwarfs. This flattening implies that most of the mass in a stellar population is contained in stars with masses within an order of magnitude of one solar mass. The low-mass end of the IMF is particularly important for determining the total stellar mass of a population, as these numerous but faint objects contribute significantly to the mass budget, while remaining difficult to observe at large distances. The shape of the IMF emerges from complex physical processes operating during star formation. Gravity and turbulence are believed to be the dominant factors determining the power law, high-mass part of the IMF. Turbulent fragmentation of molecular clouds creates density fluctuations across a wide range of scales, with the largest fluctuations potentially collapsing to form massive stars. The interplay between gravitational collapse and turbulent support helps establish the characteristic power law slope observed at high masses. The peak of the IMF appears to be primarily determined by dust opacity and molecular hydrogen physics. As a collapsing gas cloud reaches certain density thresholds, its opacity increases dramatically, trapping heat and raising the temperature. This temperature increase raises the gene's mass, the minimum mass required for gravitational collapse, effectively setting a characteristic mass scale for fragmentation that manifests as the IMF peak. Protostellar jets and outflows play a regulating role in star formation by injecting momentum into collapsing gas clumps and potentially unbinding some of the gas. This feedback mechanism may help limit the efficiency of star formation and regulate the final masses of forming stars, particularly in the intermediate to high mass range. The environment in which stars form influences their mass distribution. Late-type stars, lower mass, may arise from feedback-regulated fragmentation of molecular cloud filaments, which build up embedded clusters. In contrast, early-type stars, higher mass, form under more violent accretion and feedback-regulated conditions near the centers of these clusters. This environmental differentiation contributes to establishing the overall shape of the IMF. One of the most persistent debates in the field concerns whether the IMF is universal or varies with environment. The relative consistency of the IMF observed in the solar neighborhood and in nearby young clusters has led many researchers to adopt a universal IMF as a working hypothesis. Particularly, the position of the peak and the slope at high masses show remarkable consistency across diverse environments within the Milky Way. This consistency suggests that the fundamental physical processes governing star formation operate similarly across a wide range of conditions. Despite this apparent uniformity, several studies have claimed evidence for IMF variations in certain environments. The most prominent claims involve massive elliptical galaxies, where spectroscopic analysis suggests an excess of cool dwarf stars compared to the Milky Way, a bottom-heavy IMF. Such a modified distribution would imply a larger stellar mass-to-light ratio by a factor greater than 2 compared to a Milky Way-like IMF. Independent evidence from strong gravitational lensing and dynamical modeling of early-type galaxies also suggests mass-to-light ratios consistent with a non-standard IMF. However, the agreement between these various methods remains controversial. with some studies finding no correlation between spectroscopic and dynamical IMF estimates in nearby galaxies. The detection and verification of IMF variations face significant methodological challenges. Direct measurements of the IMF can only be made within the Milky Way, requiring indirect techniques for extragalactic systems. These techniques rely on assumptions about stellar evolution, population synthesis, and galaxy formation that introduce systematic uncertainties. Additionally, the evolving definitions of the quantity being measured and the different scales at which the IMF is applied, from individual star-forming regions to entire galaxies, have led to some confusion in the literature and potentially conflicting conclusions regarding IMF universality. The concept of the IMF applies across different astronomical scales with important distinctions. The IMF in individual star-forming regions, the stellar IMF, and the IMF aggregated across an entire galaxy, the galaxy-wide IMF or GWIMF, need not be identical. The GYMF results from the integration over all star-forming molecular cloud clumps and their stellar IMFs in a galaxy, and it depends sensitively on the physical properties of these clumps and the range of their masses. According to the integrated galactic initial mass function theory, the GWIMF depends on the star formation rate of the galaxy. This dependence arises because the star formation rate affects the range of molecular cloud masses that form in a galaxy, which in turn influences the aggregate distribution of stellar masses. Star clusters represent important laboratories for studying the IMF because they form from a single molecular cloud in a relatively short time span, approximating a single star formation event. The cluster environment adds complexity through dynamical interactions that can affect the apparent mass distribution, particularly for the most massive stars that tend to sink toward the cluster center through dynamical mass segregation. Determining the IMF presents significant observational challenges that have driven the development of various measurement techniques. In nearby regions, direct counting of individual stars remains the most reliable method for determining the IMF. This approach involves measuring the luminosities of individual stars, converting to masses using theoretical mass-luminosity relations, and constructing a histogram of the resulting mass distribution. While conceptually straightforward, this method is limited by completeness issues at low masses and distance limitations. For more distant systems, particularly extragalactic ones, indirect methods must be employed. These include analyzing integrated light through spectroscopic features, sensitive to specific stellar types, using gravitational lensing to constrain mass-to-light ratios, and dynamical modeling of stellar systems. Since there aren't enough young clusters available for direct IMF calculations in many cases, astronomers often measure the present-day mass function and extrapolate back to the IMF using models of stellar evolution and star formation history. This approach requires careful accounting for stars that have evolved off the main sequence or have been lost from the observed region. The past decade has witnessed significant growth in the number and variety of methods for measuring or inferring the shape of the IMF. These advances include more sophisticated spectroscopic techniques, improved population synthesis models, and innovative approaches to disentangling the effects of age, metallicity, and the IMF on observed galaxy properties. Paralleling these observational advances, progressively more detailed simulations of star formation have provided theoretical predictions for the IMF under various conditions, helping to interpret observational results and test proposed physical mechanisms. The IMF has far-reaching implications across numerous areas of astrophysics. Models of galaxy evolution rely critically on stellar population synthesis, which uses the IMF as a fundamental input. The assumed IMF affects predictions for galaxy colors, spectra, chemical enrichment, and mass-to-light ratios. If the IMF varies systematically with environment or cosmic time, many conclusions based on standard assumptions may need revision. The IMF strongly influences the chemical evolution of galaxies by determining the relative numbers of stars of different masses, which in turn produce different elements through nucleosynthesis. Top-heavy IMFs lead to more rapid and extensive metal enrichment, while bottom-heavy IMFs result in less efficient enrichment but greater locking of metals in low-mass stars. At low masses, the IMF sets the galaxy mass budget and the number of substellar objects that form. Uncertainties or variations in the IMF directly translate to uncertainties in galaxy stellar mass estimates, affecting interpretations of galaxy evolution, the galaxy stellar mass function, and the cosmic star formation history. At high masses, the IMF controls the number of core collapse supernovae, which are critical for energy and momentum input into the interstellar medium. The frequency and distribution of these energetic events influence galaxy-scale outflows, star formation regulation, and the enrichment of the intergalactic medium. Despite decades of research, several challenges remain in our understanding of the IMF. While various physical mechanisms have been proposed to explain the IMF's characteristic shape, a comprehensive theory that quantitatively predicts the IMF from first principles remains elusive. Future work must integrate multiple physical processes, including gravity, turbulence, magnetic fields, radiation, and feedback, into a coherent theoretical framework, establishing whether systematic IMF variations exist, and if so, quantifying their dependence on environmental parameters, represents a major ongoing challenge. Future observations with greater sensitivity and spatial resolution, particularly from next-generation telescopes, may help resolve this question by enabling more precise measurements in a wider range of environments. Extending our understanding of the IMF to the high redshift universe, where conditions may differ substantially from the local universe, presents both challenges and opportunities. If the IMF varies with metallicity or other parameters that evolve with cosmic time, this would have profound implications for interpreting observations of distant galaxies and reconstructing cosmic history. The low-mass end of the IMF, extending into the brown dwarf and potentially planetary mass regime, remains poorly constrained. Understanding the formation of these objects and their relationship to the stellar IMF may provide crucial insights into the minimum mass for star-like formation processes. The initial mass function stands as one of the most consequential distributions in astrophysics, linking the microscopic physics of star formation to the macroscopic properties of galaxies and the universe. Its origin lies in the complex interplay of gravity, turbulence, thermodynamics, and feedback processes during star formation. While evidence suggests a surprisingly universal IMF across diverse environments within the Milky Way, tantalizing indications of systematic variations in elliptical galaxies and other extreme environments continue to stimulate research and debate. Resolving the question of IMF universality versus variation remains a central challenge with far-reaching implications for our understanding of stars, galaxies, and cosmic evolution. As observational techniques advance and theoretical models become more sophisticated, our knowledge of the IMF continues to deepen, but many questions remain unanswered. The ongoing exploration of this fundamental distribution promises to yield new insights into the processes that shape our universe, from individual stars to the largest cosmic structures.